Hello, and this is problem 1 from homework 3. So you see we have two masses, big M and little m, situated in this system here. Little m is situated on a rod which can't translate x and y, but can translate can't translate x, but can translate y. And then big M is on a pulley here, attached to a string with total length L. I've denoted this L naught as the kind of intermediate length here between the pulley and little m. And then through this expression, we can get large M. So the goal of this is to use the potential energy to try to find the equilibrium state of any given position here, see if there is an equilibrium state, and discuss the stability of that. And so we can easily set up a potential energy equation here between big M and large H and little m and little h here, and we can get those little h and big H through just the geometry of the problem. So sine theta equals opposite over hypotenuse here, so B over L. Rearrange that and plug it into this formula here. You get that H is equal to L, total length of the string, minus B over sine theta. In a very similar way, we can say that tangent theta is equal to B over H, opposite over adjacent. Rearranging that, you get that little h is equal to B over tangent theta. Then we can plug both of these expressions into our potential energy equation, and we see that big mg, this expression, minus little mg, this expression, is equal to the potential energy equation in terms of theta. Now for equilibrium positions, we know that the potential energy derivative has to be equal to 0. So if we do the derivative here, I'll save a lot of the calculus for you, but this is essentially what you get here. You can pull out a cosecant term, and then you have this expression here. Now, it's worth noting that when we're setting this equal to 0, cosecant theta can never be equal to 0. So this is the term that we're most interested in. So when you set this equal to 0, you can rearrange this, and skipping a bunch of algebraic steps here, we can say that cosine theta is equal to little m over big M. Now this is only satisfied when little m is less than or equal to big M. And you can see that basically any time that little m is less than big M, there will be some position, theta, that will result in an equilibrium position. When little m is equal to big M, L would have to be infinite in order for there to be an equilibrium position, because then theta would be 0.
Cool.